In this video, we're going to look at steps for performing mesh analysis. The first step is to assign mesh currents in each of the in meshes. So you notice I've kept this general with this variable in as opposed to talking about a specific circuit that maybe has 3 or 4 or some specific number of meshes. So each one of those meshes is going to need a mesh current. So we could have I1 for mesh 1, I2 for mesh 2, I3 for mesh 3, so on and so forth, all the way up to I sub n for mesh n. Now, in some cases, the problems are going to have these mesh currents already defined or already drawn in the circuit for you. However, in other cases, you'll have to draw or define these mesh currents yourself. Conventionally, these mesh currents are going to be defined as moving in a clockwise direction. So conventionally, in a clockwise direction. But what we're going to see in some later videos is that they can also be in a counterclockwise or anti-clockwise direction as well. And so we'll talk about that in more detail later on. So let's sort of look at this simple circuit from the previous video to help us visualize what we're talking about. In the previous video, we identified 2 meshes in this circuit. We said we had one mesh here on the left, and again, remember that's a loop with no loops inside of it. And we had a second mesh over here on the right. Which one is 1, which one is 2, doesn't really matter. That's up to you in the definitions, assuming that the mesh currents aren't defined for you in the problem. So let's say we want to define mesh current I1 being in this left mesh. Well, we would draw this little loop indicating this current is moving around this mesh and label that as I1. And over here on the right, we can do this a similar thing. And notice I've drawn these both clockwise according to convention, and our I2 is going in a clockwise direction around the mesh on the right. So that's how we could define our mesh currents for this simple circuit here. And of course, if we had more meshes, we would just need more currents, one for each mesh. The second step is to apply KVL to each of those in meshes. And then once we've applied that KVL, we're going to use Ohm's law to express the voltages in terms of those mesh currents. And so of course in a later video we're going to go through in explicit detail of each of those steps within that second step there and see how it's done. But just to sort of preview that a little bit, what we're saying is we're going to use KVL. And so of course remember KVL is Kirchhoff's voltage law. And so what that says is that the sum of the voltages around a closed loop is 0. So we're going to go around this loop over here, because remember a mesh is also a loop. We're going to sum these voltages and set them equal to 0. Now of course the V1 is pretty obvious. With our R1 and our R3 voltage, what we're going to do is we're going to utilize Ohm's law like we set up here, and we're going to express those voltages in terms of our mesh currents, in this case I1 and I2. And so again, we'll come back to that and we'll see how to do that in more detail in a later video. So once we do that, we're going to have in mesh equations. And our third step then is just going to be to solve the resulting in simultaneous equations. So again, note we're keeping everything general with this variable in as opposed to looking at a specific number. So our third step is just to solve those simultaneous equations, and that's going to give us our mesh current values. So in this case, we would have 2 simultaneous equations. 2 simultaneous equations, and when we solve for those, we're going to get values for our 2 mesh currents. Now, how do we solve for that? We have a couple different ways, or actually a few different ways. The method that I'm going to recommend you use is our matrix method for solution, and there are more details about that in the notes. However, for simpler cases, we can also use linear combination, and we can also use substitution. However, as our circuits get more complex, we're going to see that this matrix method is a lot easier to implement and has a lot less room for errors to sneak in. Okay, so we've solved for our mesh currents, so you might be asking yourselves, why do we have another step? We've already solved our mesh currents. Well, in some cases, mesh current isn't what we're trying to solve for in our circuit. Maybe we're interested in a voltage or a power, or maybe some current that's not a mesh current. So our fourth step then is to find whatever other values are of interest to us. And so this step isn't always going to need to be performed, but in many cases we do have to take that last step and go one step further from our mesh currents to find whatever value of interest that we initially wanted.